Hey, so this problem is Leetcode 226 inverting a binary tree. Well, you can kind of do it using depth first search or breadth first search. And in this breadth first search series, we're going to use breadth first search. So, well, all right. So there's a few key takeaways on this problem. The number one is we will be using the 2D structure that we have imagined for ourselves, right? Instead of looking at it as a 1D queue. And second is the second key takeaway of this problem is that you can not only traverse the tree using breadth first search algorithm, right? Just traversing the tree, going through nodes to nodes, level to levels, right? But you can also manipulate the tree. And I feel like this so yeah, there's two aspects, two features to this manipulation of the tree and traversing. And this question um, focuses on more of like it's a manipulation, but traversion, the traversal of the tree is needed because you need to kind of go down the tree as you go. But manipulation is another category, seems to be another category in this in these problems. So just got to remember that. So yeah, BFS is used to traverse through the tree and also manipulate the tree. And this pattern specifically is to the inversion of the tree. Um, so the 2D structure we've been kind of playing around with, we've been imagining, or is like the key insight that to that is like we cannot read it as like a matrix. We cannot treat it like a matrix. I think like I did that mistake when I was first doing this. I was treating it like a matrix, and it didn't work. Uh, so we must treat it like a queue because essentially it is a 1D queue, but it's just in our brain that we kind of look at it as like a 2D. We project it as a 2D entity. All right, so another thing that I want to mention is manipulate tree, right? We got to manipulate the tree such that the addition of the nodes in the 2D structure, 2D matrix, is what we want. So here's what I mean by that. So if you just do the generic add operation, right? Generic queue adding to the queue operation. This is the imaginary 2D structure that will take place, or that we will end up creating. So we end up for this tree, um, we push 4 and then 2 and then 7 and then 1 and 3 and 6 and 9, right? But that's not the structure we want, right? The question says, can you give me a structure that is similar to this? 4, we push 4, and then we push 7, and then we push 2, 9, 6, 3, right? So the question is like, how can we go from the top structure, this structure, to the bottom 2D structure? Well, well, now this is where manipulating the tree before the question now becomes, how can we manipulate the tree such that when we add stuff to this structure, um, that will such that when we add the nodes in this 2D structure or the queue, the final queue will look like this. Well, what about if we just swap the nodes, right? If we just swap the nodes before adding to the queue, then this our final 2D structure will look like this, and we will have done our job. So this is what I mean. So we add 4 first, right? And then we swap the nodes left and right. So left becomes right, right becomes left, and we just do our normal thing, like normal operation. We add the left and then the right, because we have manipulated the tree before adding it to the queue or to this 2D structure. It reflects what we want. And well, we are processing, like given that we're processing 7 now, we swap it again, and then we're adding it again. So we're manipulating the tree again and then adding it only after, right? So structure will reflect like this: 9, 6. Again, now we're processing 2, right? We're the level 2, and we're processing the node 2. we want to manipulate the tree first and then adding it. So if that will uh, we'll end up with a structure like this. So yeah, this problem really, like, the key insight to this problem is really just about um, manipulating the tree before just adding stuff to the queue. So it's stacking the idea of like manipulation. We're just basically stacking manipulation on top. So, and that leads to inversion of the tree, um, like that, which is a mirror image. So yeah, that's that. And if we look at the code right now, all right. So in this code, we're kind of inverting the tree. Um, so if you look at this, this is pretty much your generic depth breadth first search. All right. We got levels over here, and then we are iterating through the 2D structure. So levels and then level length. So this for loop iterates through that row. And then we're popping the node out, and then we're kind of adding this stuff. But the special case about this problem is like we got to manipulate the tree before, just got to add it on top. Um, so the manipulation part where we're swapping the thing, swapping the two nodes, and it kind of looks like this. If we run it, so it's literally just the same, but the idea is like we can manipulate the tree before adding it, and then that results, uh, you know, we can basically we can manipulate the tree. That's what I meant. uh, by and the manipulation over here is just kind of swapping nodes. And how did we arrive? How do we know we had to swap the nodes? Well, it was a 2D structure that gave us the hint, right? What 2D structure that we wanted? What did the final queue state? What did the final queue state look like? And how? And then we kind of like went from there, right? Like, well, yes. So if we submit it, it works. But you already know it works. So let me just conclude. So it really helps if you do not know what type of manipulation to do. Really helps to kind of look at the final queue state or the 2D structure that we want, and really, and and look at the initial, like by default, the default 2D structure, the queue structure that we have, and really like reason about like how to get there. How do we get to this final queue state? And I really think that approach, and from that, automatically like the manipulation operation will fall into your hand or into your mind, and then you can just code it out. Just thanks.